All right, I'm going to go this one pretty quickly because class is going to start in like 2 minutes. So, falling bodies. Suppose a rock is tossed upward from the roof of a building, SOT. The position of the rock, assume that the upward direction is positive and no force acts on the rock other than the force of gravity. So we have Newton's second law. So Newton's second law, because, force is equal to mass times acceleration, acceleration is just the second derivative of the position function. Because it's the second derivative of the position function, we can say that that is going to be the second derivative of s with respect to time. So instead of saying mass times acceleration for our force, we're going to say mass times the second derivative of our position function, which is just equal to the negative mass times g, where this is really negative g because of the act of gravity, since it's actually pulling it downward. And so that's why we have the second derivative of s with respect to t is equal to negative g. Now, we could solve this if we wanted to. If we solve this, what we would have would be, to get back to the position function, is going to be negative 1/2 g of t squared plus the initial velocity t plus the initial position, where, this is a formula that I believe that you see in your early physics classes. The second thing is the falling bodies and air resistance. So assume that a falling body of mass m encounters air resistance that is proportional to its instantaneous velocity. Assume that the positive direction is oriented downward. The net force acting on the mass F equals F sub 1 plus F sub 2 is equal to mg minus kv. So the model that we're going to have for this is based off of, again, force equals mass times acceleration, where, again, our acceleration is just the derivative of a velocity function, so we can write this as a first-order derivative, all right? Or we can write this as a second-order derivative, where we take, our acceleration as the second derivative of our, let me go ahead and box this up, the second derivative of our position function, and we get mass times the acceleration is equal to mass times the pull of gravity minus k, that constant, minus velocity, which is our velocity ds over dt, the derivative of the position function. Again, we could bring this all over to the left side and then have all of our differentials on the left side equal to mg. All right, so those are all of your kind of models that we're going to use. If I give you an example of falling bodies, or I give you an example of falling bodies with some air resistance, then these are the formulas that we're going to use. Again, ask some questions on this if you'd like. I don't have a great way of kind of going over everything today, just because I'm holding the camera with one hand and a pen with the other.